we are going to start the lecture on nanotechnology in chemical engineering. So we have prepared various nanomaterials, that is carbon nanotubes that we have prepared, and different method of synthesis we have studied. So now various characterization techniques also we have studied. So today we will basically discuss about the Raman spectroscopy, UV-vis-NIR spectroscopy and DLS spectra. So these are the very useful characterizations or techniques. So that can be used means whether the nanomaterials whatever we have prepared, so that is in the form of solids or in maybe ionic states in liquids or maybe in solutions that is present the nanomaterials. So that particular size means if you want to know means that nanomaterials we have prepared in nanofluids, that nanoparticles we have distributed in any nanofluid. So the particle size if you want to know, so sometimes that is useful in the help of DLS spectra, or UVs means ionic compounds is present or not. So Raman spectroscopy is very useful for carbon nanotubes. If we are able to prepare for a specific method, so then we can check that. So this is the basic about the spectroscopy. Few things will be discussed, so not more details. So this is the Raman spectroscopy. It looks like. So Raman spectroscopy, in Raman spectra we can use means suppose a molecules having a stretching frequency, that is symmetrical stretching, so that we can some vibrations is there, so we can measure with the help of Raman spectroscopy. It is complementary with the complementary techniques with the FTR spectroscopy. So in FTR spectroscopy you usually get symmetric asymmetric stretchings that is being present in that particular molecules, and whence there is a symmetrical stretching in that molecule, so that is not IR active. So then we have to use Raman spectroscopy to get that means molecular vibrations. So here different excitations means lasers we can use 532 nanometer, 785 or 1064 nanometer, different wavelengths we can use for this incident radiations as the source of lights. It is actually based on scattering phenomena or electromagnetic radiations that is scattered by the molecules. So the scattering means when that electromagnetic radiations fall on molecules, so light will be scattered from that molecules, and that scattering may be different types. So that scattered light we can collect with the help of detectors that is present in IR spectroscopy, and we can analyze that material property. Okay. So here scatterings may be elastic scattering or inelastic scatterings. Elastic scattering is called Rayleigh scattering, and inelastic scattering, that is two different types, Stokes scatterings or anti-Stokes scatterings, in whence radiations scattered with the frequency lower than that incident beam. So then it is called Stokes scattering, and most of the cases in Raman spectroscopy Stokes scatterings is being used. Here is the signals that we get much more stronger than anti-Stokes scatterings. In anti-Stokes scatterings the frequency radiations with the frequency with higher frequency, that frequency coming out from the samples will be higher than the incident beam. So here's different virtual energy states is showing. This is energy states, this is Rayleigh states, Rayleigh scatterings or Rayleigh lines. So here's both are having same frequency. In case of the Raman scattering use Stokes scattering, so this is incident, this is scattered light intensity. So you can see, so and in case of the anti-Stokes, so this is started from the molecules, and that scattered light intensity is much more higher than incident radiations. So here I said the Stokes scattering is much more 100 times more intense than anti-Stokes. So this is actually used for Raman spectroscopy. Okay, so here the Raman shift we get from the Raman spectra that will get, that is usually 3 or 50 to 300 3000 centimeters inverse, the Raman shift that usually gets. So here's inside of that equipments you can see that samples we can place here. Laser source is there, laser will pass, then with that samples it would be interact and then come back to the detector, so we can get Raman signals. Okay, so when molecules having I said symmetricals in structure, so then that molecules would give Raman active signals. So when in case of the IR, so there is changes in dipole moments in that molecules when electromagnetic radiations interact with the molecules, but in case of the Ramans when molecules there is no dipole moment change, but induced dipoles that would be changed in that molecules when electromagnetic radiations or that fields will be interact with the molecules. Okay. So this is express the induced dipoles that would be changed, and molecules always having some symmetrical structures, no asymmetric structure. So then some distortions would be there when electromagnetic fields that would be applied in that molecules. So here this is the electric field and applied electric fields, and this is the change of induced dipole moments in that molecules. Here alpha is the polarizability, that is the constant. You can see, so here's examples I am showing. So when electric field is placed, molecule is placed in electrical field, so what kind of changes is present in the molecules. Let's say hydrogen molecule, this is symmetric molecules, so that is placed in electrical fields. This is across the bonds and this is along the bonds. So field is, this is field, electrical field, this is across the bonds. So this type of changes, so when electric field is passing through that molecules through along the bonds, so then this type of polarizability will be changed in that molecules when along the bonds. So this type of polarizability that would be changed in that molecules, that would be means actually gives induced dipole change in that molecules, and that would be active for Raman spectroscopy, or with the help of Raman spectroscopy we can get. So different type of molecules we have taken, so water molecules or chloroforms. So when that is placed in electrical fields, then there is change is polarizability of that molecule. So this types or changes in case of the water molecule, or in this type of molecules also this type of polarizability changes in that molecules actually in place of when it is placed in electrical field. So then two poles would be theirs, and then electrons would be moved towards positive poles and negative poles. By that way that changes we can say that is induced, not very strong. So induced dipole changes would be there in that molecules. Okay. So I said when symmetrical stretching is present, see here one water molecule is taken. So when there is symmetrical stretching is present, so then Raman should be active. So Raman active signals we can get with the help of spectroscopy. When there is a bendings or stretching, asymmetric stretching is there, that we cannot get with the help of Ramans. So only symmetrical stretching changes, vibrational changes, that we can get with the Raman signals. And so when bending or and asymmetric stretching is present, so for that we have to use IRs. Okay, so these are IR actives and these are Raman actives. Okay, so here's Ramans and IR comparisons is showing. So when molecules having symmetrical stretchings, Ramans would be actives, IR would be inactives. When bendings or asymmetric stretching should be there, so then Ramans would be inactives, however IR would be active. This is the mutual exclusion principles. You can set that it is means actually complementary techniques. So means some informations we get with the help of Raman and some informations we get from IRs. So here's one comparisons of IR spectra and Raman spectra, you can see. So here's for the same molecule CH3 was taken. So here you can see this particular band is IR strong signals we are getting, but in case of the Ramans we are getting very weak signals. And here's the other signals. So here also this is also IR strong, but Raman is weak signals we are getting. So here's this is Raman signals we are getting very strong, but here we are not getting IR signals. So these are the complementary to each other for the same molecules. Two different spectroscopy gives two different type of informations of that same molecules. Okay, so here's few, let's say a nano catalyst was taken. Let's say nickel ceria alumina catalyst, nano catalyst that was prepared. For examples we are showing how Raman shift and intensity that we are getting in case of the nano catalyst that was used for the preparation of multi-wall CNT preparation. So here this catalyst was used, and then H4 was passed through these samples, and then at high temperature, so multi-wall CNT was deposited on the sample. So you can see when pure catalyst or materials this nano catalyst was taken. So here these are the Raman spectra we are getting 460, 626, two different locations, even 110 also we are getting sometimes. So in reduced catalyst, this is calcine catalyst. So it is when the materials is calcined means metal oxide bond is present. When it is reduced, so most of the metal oxides will be converted into metals and few remains there. So what are the metal not converted that we can get, that is, let's say ceria, CEO2, that would not be reduced at this particular, means when it was reduced in case of the nickel oxide, that may be converted into nickels metals, so partially. So here nickel oxide signals we can get 626 and at this particular locations, and ceria we are getting at this particular metal oxide, means ceria oxygen bond vibrations, so that we can get 460. And so when this materials was used are said for CNT preparation, so after that, so you can see here, means here strong signals are present for in case of CNT, that is forms DG bands, 2D bands that we are getting once that materials was used for CNT preparation. So once CNT was deposited, that materials was analyzed with the help of Raman spectroscopy. Raman signals we are getting, okay, Raman spectra we are getting, and that we are analyzing. So here's the metals oxide whatever is present, that is not exposed, so that is why you are not getting. So means metals or catalyst, this is it was metals oxide, so that was whence that was not used for that CNT preparations. Metal oxygen bond vibrations we can get, here strong signals we are getting, and when CNT was deposited so over the materials or catalyst, so then only CNT, exposed CNT we are getting by this, and we are not at inside of this CNT there is metal oxide is present, or this catalyst that is not getting here actually, that is covered by that CNT. So that is why at this particular point metal oxide bond vibrations is absent. So if we are able to separate out this CNT, then again here's ceria or nickel oxide whatever the signals that we can get. Okay, with the help of Raman spectroscopy we can get a specific bonds a particular locations, so or signals. So here 460, so after that materials image we can get Raman image what is called, so visualizations and distributions of that different metals or materials that is present in that particular sample, so that we can, or that space is present in that sample, so we can get an image. So with the help of Raman spectroscopy that image also we can study. Okay, so next is the UV spectroscopy, that is also very useful when suppose you have prepared some nanomaterial that is present in solutions or maybe in terms of solid also, so that we can get with the help of UV-vis visual spectroscopy and we can analyze that. So here the absorption wavelengths each 100 to 700 nanometers within that range, so it is actually UV range and visible range. So two ranges are there, so that is why it is called visual spectrophotometer or spectroscopy. So with this spectroscopy we can quantitatively as well as qualitative sample analysis we can do. So what are the components present and how much concentrations so are present that we can get. So here's the basic principles of this theory, that is for this Beard-Lambert law is used for this. So here the absorptions, here incident light that may be UV-vis that is passed through this sample, this is sample. So then this is incident light, this is transmitted light, rest would be absorbed. So then absorbance we can find out that directly proportional to the concentrations and length, path length. Okay, this is the path length. So we can find out that absorbance are UV spectra and that we can analyze. Okay, so these instruments details. So usually the instruments UV spectroscopy, single beam UV spectrometer or double beam UV spectrophotometers, two types is available. So here's in instruments we can see the source, radiation source means ultraviolet visibles, that ray that would be developed, some lamp is there, so that is the source, tungsten halogens or quartz halogens, quartz iodine lens is present, that is the source of this IR UV ultraviolet visibles source. Then monochromator is there, gratings, sample holder, detectors, amplifier and computer is present. With that help of that we can get signals of that particular spectra of that materials, nanomaterials is present in that particular solution. So here is the sample compartments, here we can place any samples that we have prepared, that is very dilute concentrations we can use here. This is the light source. This is for actually single beam UV spectrometer. So here the light will pass through the samples, come to the detector. In case of the double beam UV spectrophotometer, this is the source of light, this is the beam splitters, and then one light will pass through this, another will come directly. Here is the sample compartment, here is the reference. So here will get I, here will get I0. So then simultaneously we can get the UV signals or spectra for that particular materials present in the form of liquids. Okay, so here absorbance we can get, and here's wavelength we can get. Okay, so here simultaneously we can measure with the help of reference, both we can place together. And here first we have to put the reference samples, and then we have to put the samples. So by that way we can get the samples analysis. This is actually UV spectrophotometer looks like. So I said UV-vis-NIR spectrophotometer. Here also ultraviolet visible, with that NIR range also we can include. So then up to 200 to 2500 nanometers, within that range we can get in this equipment. So depending upon that manufacturer, there are many manufacturers are there. So depending upon that, this is actually showing carry 5000 variants. Depending upon that manufacturers and available equipments, either we can get UV-vis or UV-vis-NIR. So depending upon range, so here full range, so 200 to 2500 nanometers within that wavelength, and here's 200 to 750 nanometers within that range, and here's 200 to 2500 nanometers wavelengths within that range we can use. So here's basic already have discussed. So here's this UV spectrophotometers. Here also we can analyze the samples 3D many modes. So transmission modes for liquid samples, ATR mode also we can do, specular DRS modes also we can do. So this is for actually solid sample, and this is for liquid sample. So here's liquid solid both we can analyze, so depending upon that materials we have. So here's cobalt nitrate was taken. So cobalt nitrate, that is the cobalt crystals, actually that is solids, that was mixed up with the alumina at ambient condition. This spectra was taken actually. So x-axis you can get wavelengths, y-axis you can get absorbance. So here's in this materials cobalt plus 2 ions present, nitrates present. Nitrates we are getting in that range, cobalt plus 2 ions we are getting in that range. So different locations which water is present also, that usually come at NIR range actually. So this is NIR range, after that 750. So after this is NIR range actually. So here some water molecules you can get near infrared, so in that range. Okay, so this is actually DRS accessories, DRS, diffuse reflectance spectroscopy accessories. So that can be used for measurement. This is cuvette for liquid sample analysis, and this is for solid sample analysis, and this is praying mantis it is called. So we can put our sample, solid sample here placed over there, and then UV-vis-NIR spectra we can get. Okay, so here 3 different materials was taken. Let's say alumina was taken, we have passed UV-vis-NIR through these samples. Here let's say alumina, and then so we can get this type of signals. There is no electronic transition, so here's alumina usually don't give. So when it was cobalt, here's cobalt oxide was placed alumina, or this is nitrate salts we can place here. Plus 2 oxidation state of cobalt is present. So here's cobalt plus 2 you can see, and when it is CO3O4 in the solid powders, so this type of spectra you can get. Okay, so this signal is different from this, and here's nothing is present. So whatever the in this materials, so if combinations of alumina and cobalt is present in these samples, so for cobalt alumina nothing, no transitions is coming. So here's whatever the transition that is coming, so that is due to the this cobalt CO3O4, means metal oxide is spinel type of oxide is present, and here's cobalt nitrate we are using here only due to the cobalt plus 2. So this is D block elements or metals. So here that electronic transitions in the due to the lone pair electrons is present in the d block d orbital. So that would be electronic transitions, and we can get this type of signals. Okay. Next is the dynamic light scattering. So that is also very useful technique for the nanomaterial characterizations. When and suppose you have a nanomaterials that you have prepared in the solutions, let's say nanofluids we have prepared, means where nanomaterials that may be Fe2O3 or cobalt oxide, copper oxides, any metal oxides, iron oxides that is present in solutions. So in solutions different nanomaterials present, nanoparticles. So with that also some surfactants, polymeric materials also we can use to stabilize that nanofluids. So then stable nanofluids or nanofluids we can prepare. So base fluid is present, and with that nanomaterial should be present, and with that also sometimes to make it more stabilizations of that fluids or nanomaterials will be stabilized in the base fluid. So sometimes we can use some surfactants also. So that nanomaterials may be very small in size, sometimes agglomerations also would be there. So larger particles will formations is there, as a result stability will be down after 30 days, 25 days. So that is very important. So to measure the size of the nanoparticles, whence that is some micro range suspended in a liquid. So this technique is very useful, dynamic light scattering techniques that can be used to characterize the materials we have prepared, nanomaterials in solutions or maybe in nanofluids. So then we can characterize, okay, to measure the size of the nanoparticles of some micron range that is suspended in a liquid. Okay, so whence that molecules presents nanomaterials in that particular liquid, they will move depending upon their size, charge, they will move different velocity. Okay, so means that molecules moves in that solution, that is due to the Brownian motions. Okay, randomly that particles moving inside of that liquids. Okay, if the particles is large size, then Brownian motion should be slow. When the particle is very small particles presents, then that movements of that particles in that particular fluids or solvents would be very fast. Okay, so either the particles may be smaller or larger, depending upon that their Brownian motions or movements will be changes. Okay, also the temperature is very important parameter. So means viscosity of that solvents that present. So viscosity that depends or changes with the temperature. So if we means increase the temperatures, viscosity will be down. If we means decrease the temperature, viscosity will increase. So therefore the instability of that nanoparticles in that particular solvent, so that creates some means depending upon the temperature, whether it is low or high temperature, the convection currents, that means molecules will move in that particular solvents. So means movements will change depending upon that temperature. So solvent or that solution temperatures we can change, and then movements will change also. Okay, see here hydrodynamic diameters, that is the particles or nanomaterial that is present in particular solvents. So we can measure the hydrodynamic diameters of that particle by DLS techniques. So here this hydrodynamics we can measure using this equation. This is called Stokes-Einstein equations. Here K is the Boltzmann constant, is the temperatures, absolute temperature, and it is the that viscosity of that solvents, and D is the translation diffusion coefficient, since molecules is moving from one point to the another point. So then each diffusion is there, diffusion coefficient is important. So that particle that is moving from one point to the another point, that is called translational diffusion coefficients, that can be expressed in terms of D. So that depends on the size of the particles, surface structures, speed, concentrations, and type of ions that is present in that medium. So depends on that diffusion coefficients that will changes in that particular solution. So in that equations, Stokes-Einstein equations, here's if you know the viscosity, diffusion coefficient, temperatures, so we can find out the particle size of that we have prepared that solutions. Okay, so many factors that affect the diffusion speed. Means speed means here's actually means diffusion coefficient. So we are measuring, so diffusion coefficients affected by different factors. So here's ionic strength. So ionic strength in that mediums, that may be low concentrations or maybe high concentrations, depending upon that actually that would affect the diffusivity or diffusion coefficients of that materials present in that particular solvent. So actually low ionic strength, that would be the slower diffusions, therefore larger hydrodynamic size would be there. Okay, so here hydrodynamic size, that would be larger when low ionic strength present in that particular solvent. When it is high ionic strength that is present, then movements of that molecules or nanoparticles will be faster. So then when it would move faster, then smaller hydrodynamic size would be smaller. Okay, so at the same time surface structure also I said. So when we prepare say nanomaterials in nanofluids that would be dispersed in a fluids, and nanofluids we are preparing, so they are sometimes we use some polymerics or surfactants, so that would be covered the outer surface of that nanomaterials. So that polymeric particles, that would also affect that speed of movements of that Brownian motions, whatever that is present in that particular molecules, that would change. Okay, so when adsorbs layers or polymer surfactants adsorbs on the surface of that particles, that slow the diffusions. Okay, also shape of that particle, so means usually in case of nanomaterials that is dispersed in any particular solvents in nanofluids, so we usually consider it is as a spherical fluids, a spherical particle. So sometimes that may not be spherical, that may be a rod or split type of, so that also would affect the diffusions. Okay, so therefore the hydrodynamic diameters also would change, alters, that would change. How DLS works actually? So here's in DLS we have actually through DLS we are measuring the Brownian motions of that particle that is suspended in that particular liquid, and through that we can determine the hydrodynamic size. Okay, so here's light scattering. So when suppose you have a laser source, here is the samples, through that light will pass. Okay, so here's particle concentrations, particle size, that would affect overall that light will pass through that. Okay, so here's light scatters that will pass through that, so that will be fall on that samples, means nanomaterials, and that would be scattered. Okay, so in different directions, so that would be collected and that would be measured. Okay, so speckles, patterns, formations, fluctuations of particle size, data collections, and auto correlations functions there is there. So that means actually here if you go into the systems, so it means about the instrumentations, this is the source of lights that is called laser, and after that here is the detector. So these are the detectors, so that light will be, here is the samples, this is the laser source, this is the samples, and this is the detector. So here's once light is passed through the samples at different angles, it would be diffracted or scattered. So, okay, so the scattered light will be collected, and then with the help of computers or analysis we can do. Okay, so here's the intensity of fluctuations for large and small particles. So means what are the nanoparticles or nanomaterials that will prepare, that is present in that nanofluids. So in that fluids, that particles may be smaller or may be larger. So when light will pass, so light will pass, so then we will get this type of means changes of intensity, fluctuations of intensity. If the particles is larger particles and this is smaller particles, in this case of smaller particles, so the fluctuations are with the times we can get. So for larger particles moves more slowly, therefore we can get slower fluctuations. So here to this fluctuations is very slow, but here to you can see small distance. So when smaller particles, that would move fast, and then there is the signal intensity fluctuation that would be very rapid in case of smaller particles. In case of the larger particles, the fluctuations would be comparatively less or lower. Okay, so here's the scatterings incident light that will be passed or that will be strikes over the nanoparticles, that would be scattered. So different type of scatterings, two different types. One is the Rayleigh scatterings. So when particle size is less than 10 times of the light wavelength, so then the scatterings we can get Rayleigh type of scan. This is Rayleigh type of scatterings. So when particle size is less than 1/10 of that incident light wavelength, so then we can get Rayleigh types of scatterings. When particle size is greater than 1/10 of wavelength of incident lights, then my type of scatterings we can get either this or this type of. So hence that also depending upon the particle size, whether it is smaller or larger type of particles that is forms or we have developed in that nanofluid. So, depending upon that scatterings also would be different. Okay. So, in this particular DLS technique, dynamic light scattering techniques, it has some limitations. So, it does not measure the particle size above 5000 nanometers, and it is very sensitive to the solvents having viscosity and temperature. So, means solvent viscosity temperatures means also if we vary, so then DLS means spectra that we will get, so that will also changes. Okay. DLS is known for a low resolution technique that cannot separate closely related molecules. Okay, and limited for transparent sample preparations. Whatever the samples that you have to prepare must be transparent. If it is highly concentrated, then it would be difficult for to get the spectra. Okay. Also the DLS relies on the size concentration of the nanomaterials that is present in that solutions. Optimization's concentration range is very essential, means neither very low neither very high concentrations we can use. So, an optimization of the concentration range is very important. So, it is also time consuming techniques. So, exclusively slow for slow dynamics, lack of sensitivity and process for low signal strength. So, here's two different type of materials you have taken, large particles and this is small particles. So, here the light that will pass through that sample. So, here scattering light fluctuations you can see, and when particles is large particles, after that autocorrelations functions if you do, this would comes and then we can get particle size distribution. So, within that range diameters we can get, and when small particle is there, so scattering light fluctuations you can see very fast since the molecules is very smaller, and then we can do the autocorrelations functions that will get this, and then we can get diameter of the particles, smaller diameters, this is larger diameters we can get. Okay, x axis is diameter. So, depending upon the different size of the particles, either it is smaller or larger type of particles, so we can get that this type of fluctuations of intensity of fluctuations in that spectra. Okay. Okay, so we have studied Raman spectroscopy, UV-vis-NIR spectroscopy and DLS spectra. So, DLS study, so for nanomaterials, whether it is in the form of solids, liquids that is suspended, means in nanomaterials that we have prepared in nanofluids, that is in the form of solids that is dispersed in any liquids, or maybe in the form of ion that present in that solution that we have prepared the nanomaterials that we can analyze. These are the characterization techniques are very useful. So, okay, so once we study the different applications, once nanomaterials we have prepared and then we discuss about the applications, then that would be useful. These are the various characterizations would be useful to characterize that materials we have prepared. So, okay, so thank you. So, today is up to this. Okay.